Good evening, good afternoon, good morning, wherever you are at whenever you see this. In this lesson, we want to show closure under addition following Peano's axioms for the natural numbers. And to do this, we're going to use an induction on a variable y. So we will use the Peano's axiom number 5, which is the method of induction, on the variable y to show that it is closed under this operation. Now, earlier, you may notice that by definition, in order for an operation to be called an operation, we would require it to have closure. But to show that the natural numbers are in fact closed under this operation, we will begin with that explanation or that show using induction. Okay, so let's define our set M. We're going to define our set M to equal the set of numbers in Y that are natural numbers, such that X plus Y is also a natural number. Okay, this is the set we're trying to show. We're trying to show that the sum is indeed within the set of natural numbers, and so we define our set to be that. Okay, so this is the big step, the starting point there. Sorry about the coffee stains here, but you know it's not a paper by me if it doesn't have coffee stains on it. So let's go ahead and establish then our base case. And I'll initiate it here with the ABS. If I was doing a more formal proof, I would write all this out, of course, but this is kind of like the formal, informal scratch work for a more of a formal proof. So we're going to let we're going to let y equal 0. And then in that case, we have x plus y, but in that case, y is 0. And by definition, 1 of addition, the operation of addition, that is exactly identically equal to x, which is in the natural numbers, since we assume that x is in the natural numbers as well. And x plus 0 is obviously equal to x, so that's also in the natural numbers. Okay, so that establishes then the fact that M is not equal to the empty set. Okay, and it has at least one element in it. So that's a great start. Now we're going to use the induction hypothesis here. Okay, so for the induction hypothesis, remember we're doing induction on M, or on Y. So we're going to assume that Y is in M. Okay, thus X plus Y is in M. That's the induction hypothesis. Okay, and what we want to show is that X plus the successor of Y is also in M. That's what we're going to try and show next. Okay. All right. So to begin that, then the induction step is, of course, to start on one side and hopefully we'll get to the other. So X plus the successor of Y. Well, by definition 2 of addition, we know that X plus the successor of Y is equal to the successor of X plus Y. And by the induction hypothesis, X plus Y, I guess I'll write note, by induction hypothesis, X plus Y is in the natural numbers. Okay, which means that this number, whatever this is a natural number. Okay, so I'm going to call, just for the sake of clarity, I'll let X plus Y equal Z. And so we have the successor of Z. Okay, but the successor of Z by axiom 2 of Peano's axioms guarantees that this is a natural number. In other words, the axiom 2 says that every natural number is the result of a successor of a natural number. Okay. All right. So this is by axiom 2 of Peano's axioms. Okay. And so we have then that the successor, so the successor of Y is in M. Okay. By the principle of mathematical induction, I'm abbreviating here for space, mathematical induction, the set M, then M is identically equal to the set of natural numbers, which shows then that for all values of Y in the natural numbers, the operation of addition is closed. All right. I hope that was helpful, and I'll see you in the next video.